Hi everyone, this is data mining paper presentation. We are group 8, and this is online of our paper presentation. Today I will present a paper titled Explainable and Interpretable Forecast on Non-Smooth Multivariate Time Series for Responsible Gameplay by Tashan Jagger and colleagues. This work addressed a pressing real-world issue, detecting early signs of overindulgence in online gaming, excessive time or money spent in games, particularly in skill-based gambling platforms like online roaming. It can cause significant harm to players' mental health and finances. While most modern AI models focus on maximizing accuracy, this paper argues that explainability and interpretability are equally important when the goal is timely human intervention. The authors emphasize that player behavior in gaming is inherently non-smooth and random. For example, a player who just lost might keep playing aggressively, while a big winner might quit the game. This contradicts the assumption made by typical time series models like Transformer, which often rely on smooth linear temporal dynamics. Moreover, in this high-stake context, a model isn't useful if it simply predicts risks without explaining why. Both interpretability, being able to visualize and understand the trajectory, and explainability, knowing which features contribute to the risk, are crucial for building trust and enabling interventions. To address this challenge, the author proposed the Actionable Forecasting Network (AFN), a novel architecture with 3 core components. The first one is transition module. Models psychological state transition using a deep marker model. These latent states capture the player's hidden intent and emotional patterns. And the second one is VAE-SOM, a conditional variational autoencoder that embeds the time series into a 2D SOM grid, enabling interpretable trajectory visualization. And the last one is Intelligent Forecasting Module, IFM, an LSTM with an attention mechanism to make predictions, augmented with a damping factor network to handle sudden behavioral shift and preserve interpretability. Together, these modules form an end-to-end system capable of handling non-smooth, noisy, real-world time series data. For this one, pictured is AFN architecture. One of the paper key insights is the use of Markovian assumption to capture players' psychological evolution. The transition module discretizes latent behavioral states and track how they evolve. This allows AFN to detect subtle behavioral shifts that precede risky gaming patterns. For example, a player's gameplay over several days is clustered into psychological states using cognition net. These states are then fed into the next layers, conditioning how future behavior are interpreted. This component is critical for dealing with irregular and multi-source data that cannot be modeled with single process assumptions like in weather or electricity demand forecasting. The use of self-organizing map SON is what makes AFN particularly interpretable. By mapping high-dimensional latent vector into an A-core A2D grid, AFN allows practitioners to visualize the player's behavioral trajectory, both past and predicted future. Each SOM cell represents a behavior cluster, and color indicates risk level, like red equals high risk. If a trajectory moves towards darker regions, it signals overindulgence. The model's interpretability isn't just theoretical, it's visual, tangible, and useful in real-world settings. This 2D embedding is also robust to randomness thanks to the VAE's conditioning on the psychological state. AFN blends temporal attention and SHAP values to achieve explainability. The attentional layer highlights time steps that strongly influence prediction. SHAP is then applied to features that these critical moments to determine what exactly drove the forecast. For example, if the attention is highest on day 10 and SHAP identifies add cache failure and win ratio as dominant feature, then latte and lows behaviors are prime targets for intervention. This dual-layer explanation ensures that forecasts are not just black box alerts but come with actionable insights. The author tested AFN on gameplay data from 200K players, each tracked over 90 days with 19 behavioral features. They show that AFN has improved precision accuracy by 25% over strong baselines like XGBoost and ARIMA, and detects risky behavior up to 4 weeks in advance, which is a huge window for intervention. And the last one, reduce overindulgent players' volume by 18% through feature-based simulation. And they also conducted population studies showing that removing any core module, like the transition module or damping network, leads to noticeable drop in performance. And this is the evaluation of AFN performance and others models. However, AFN is not without limitation. The first one is generalization is uncertain, as the model was only evaluated on internal proprietary gaming data, and the fixed A cross A SOM grid may not capture more complex behavioral subtleties. Modeling psychology with Markov state is simplification. It may miss long-term memory or meta strategy that players adopt. And here are the few questions I would love to ask the authors. The first one is for sensitivity to SOM settings. How does performance vary if the SOM grid is resized or the number of condition state is changed? And for the second one is focus on generalizability. Could this architecture be adapted to healthcare or financial risk prediction, where behaviors are also non-smooth? And the last one, when forecasting several steps ahead, do SHAP explanation remain stable and trustworthy?
And now let me continue to present the title MLP-Mixer, all-MLP architecture for vision, and this is proposed by Toskin et al. In 2021. And for decades, convolutional neural network have been the standard for computer vision. And recently, transformer-like vision transformer (VIT) have emerged, and it uses sub-attention layer for global contexting model. And although these two models have strong performance, but do we really need convolutions or sub-attention at all? So the author proposed a simple alternative model called multi-layer perceptrons. And it uses a simple architecture that has no convolutions, no attention. And in this model, this is the image of the model, and it split into non-overlapping patches and projected linearly. These are perceived through multiple mixed layer composed of token mixing MLP for spatial information and a channel mixing MLP for per patch features. And the final outcome goes through global averaging pooling and fully connected classifier. The entire model relies only on standard MLP operation like metric multiplication, GELU activation, and layer norm. No convolution or attention. And this is the technical details. The architect treats the input as a patch times channel equals to 2D table. Token mixing MLP are applied per channel. This is column-wise, enabling special communication. And channel mixing MLP are applied per patch, which is rule-wise, enabling feature mixing. This design is isotropic. All layers have the same shape, which is simplified imputation. Unlike VIT, MLP-Mixer have linear complexity with respect to image size, making it computationally efficient. In the experimental result, the author evaluated this model on multiple datasets, including ImageNet, CIFAR, and Flowers, and VTAB. And the author finds the result that on the large data set, MLP performed competitive with VIT and resonant, and the accuracy achieved 87.9% on ImageNet. And it also delivered higher throughput than VIT and VIT at smaller accuracy level. So you can find this on the top right picture. This model has several strengths because it is the first architecture to achieve competitive vision results without convolutions or attention. This is its novelty. And it uses only basic MLP and metric operation, and is much simplified. And it offers strong accuracy to compute throughput trade-off, which is efficient. And it performs better as data sets increase, particularly on large-scale data in scalability. Although this model has several strengths, there are some weaknesses too. The model relies on large-scale data to perform well. It tends to overfit on small data sets, and it lacks inductive bias like locativity and translation invariance, which helps CNNs generalized better in low data setting. And it's unclear how well it generalized to test outside image classifications. So there are 3 questions proposed to the author. What kind of feature do token mixing MLP learn? And are they interpretable like CNN filters? The second one is, how does MLP-Mixer perform under distribution shift or adversarial attacks? And the third one is, could this architecture be extended to sequence modeling in NLP audio? So what changes would be needed? And then it continued to the third one, interpretable emotion analysis based on knowledge graph and OCC model by Shou and al. So in this work, we proposed an explainable framework for emotion interfacing in text. The key idea is to bridge psychological emotion theory with modern knowledge representation techniques. Specifically, we integrate the OCC model, a well-established theory of emotion from cognitive psychology, with 2-layer knowledge graph architecture. This integration allowed us to translate abstract emotional logic into a structural reasoning path, which means we can trace how the specific emotion was triggered from text. Unlike many existing machine learning approaches, our system doesn't rely on trained data. Instead, it refers emotion through predefined rules and concept mapping. This result is a set of emotion triples, such as agent, emotion, object, which are both interpretable and align with the psychological reasoning. We tested the model across various datasets and found that it achieved reasonable accuracy and high interpretability, even in complex or ambiguous text. So why do we need this framework? What problem are we solving? Most traditional sentiment analysis models are limited to predicting polarity, positive, negative, or neutral. While this is useful, it doesn't answer the deeper question: why does someone feel that way? Human emotions are rich and complex. They are triggered not just by keywords, but by events like winning the lottery, action of others like betrayal, inherent quality of object like something disgusting or lovable. The OCC model helps us address this complexity. It offers logical rules for how emotion arise from interaction between people, events, and objects. To make these rules computable, we use a knowledge graph structure which enables machine reasoning and human-level interpretability. In short, our motivation is to go beyond black box model and build systems that can actually explain emotions, not just label them. Now let's look at the overall structure of our framework. Our approach is modular. It consists of 8 main components. The first one is entity recognition, which identifies people, location, organization, or other entities in the text. And then move on to emotional token detection, using affective lexicons to find words that carry emotional meanings. The third one is predictable extraction, to identify verb or action that describe what's happening. Then is sentiment polarity classification, which apply example classifier to determine overall sentiment. And then the number 5, event detection, recognizing when event occurs that may trigger emotional reasons. Agent mapping is linking entity to their rules as actors or experiencer of event. And then the object pin connecting nouns or entity to concept in our emotional schema. The last one is emotion interface, using the logic from the OCC model to reason about which emotion are triggered and by whom for what. Each step builds upon the previous one, and each model can be improved or replaced without affecting the overall logic. This makes our system both powerful and flexible. Now let's zoom in the first layer of knowledge graph, the concept layer. This layer encodes abstract logic of emotion as defined in the OCC model. We organize it into the hierarchical schema, often referred to as an emotional tree. At the top, we classify emotion into three categories based on their origin. Event, assembled by desirability, leading to emotion like joy or distress. Agent, evaluated by praiseworthiness, producing emotions such as pride or reproach. An object judged by appealingness, resulting in liking or disliking. Each emotion is represented not just as a label, but as a logical condition that can be matched against the real-world scenarios. This logic trees becomes the foundation for reasoning in our system. It tells the machine when an emotion should be triggered based on what kind of event, action, or object is involved. And then move on to the second layer, the case layer. And this layer is capture real-world task instance using NLP tools such as Stanford and ERPOS tagging. We extract entity, event, predicate. Each extract element is mapped to its abstract type in the concept layer. Once mapped, we can perform emotion interface by traversing the logical rules in the concept layer. The output of this process is a set of emotion triples, structured as subject, emotion, object. For example, Mary won the lottery. Mary feels joy due to the desirable event. These outputs are not only interpretable, but also grounded in a psychological valid theory. Finally, let's take a look at how well this framework performs in practice. We test our system, both open domain dataset and literally test. In the open domain data, the model achieves high accuracy and F1 scores. This is because name, entity, and event trigger are more clearly defined. In drama tests, accuracy drops slightly due to ambiguous pronoun, dialogue structure, and implicit emotion cues. However, the model still maintains consistent reasoning and output quality. And what's the strength of the paper? First, in terms of novelty, this paper introduced a unique combination of cognitive psychology and AI by integrating the OCC emotion model into a two-layer knowledge graph. While many studies in sentiment analysis focus on statistical model, this work built on a well-established human emotion theory and make it operational through symbolic reasoning. Second, the technical base sound. It presents a clear model framework for emotion interface, with 8 components that work in a pipeline. From entity recognition to emotion interface, the logic is derived entirely from predefined rules, which means no training data is required. This is quite rare in modern NLP. Finally, in terms of significance, this research opened up new possibility for explainable AI in effective computing. Rather than simply labeling emotion, it provides a traceable reasoning process for how emotions arise. This has potential impact not just in NLP, but also in human-computer interaction, educational AI, and psychological modeling. And the weaknesses and limitation of the work. First, while the symbolic and rule-based approach is interpretable, it may struggle with scalability. The model depends on handcraft rules and semantic mapping, which might not adapt well to informal language, social media, or multilingual text without extensive adjustment. Second, the evaluation shows reduced accuracy on drama text, largely due to error in name entity recognition and event detection. This highlights the system dependency on external NLP tools. If the upstream extraction fails, the emotion interface will be incorrect. The last one is emotion type. Without capturing emotion intensity, for example, mild disappointment and sadness, are both treated simply as negative emotion. Incorporating a scale of intensity can make the output more nuanced and closer to real human emotion. And here's the 3 questions for the author. First, how well does the model handle ambiguous or implicit emotion context? The second, could this framework be extended to multi-model emotion analysis, like video plus text. The last one is how would you adapt the model for cross-cultural emotion reasoning. And that's all for our paper. Thank you.